Hey everyone, welcome back, and today let's solve Leetcode problem 1368 titled Minimum Cost to make at least one valid path in a grid. So we're given an m by n grid, and each cell of the grid has a sign pointing to the next cell that we should visit if we're currently at that specific cell. Now the sign of grid at index I index j can be expressed as either a 1, which would mean that we have to go to the cell to the right, meaning go from grid at ij to grid at ij plus 1, or it could be expressed as a 2, which means that we'd have to go to the cell to the left, which would mean go from grid at ij to grid at ij minus 1. It could also be expressed as a 3, which means we'd go to the lower cell, which would be grid at ij to grid at I plus 1j. Or finally, it could be expressed as a 4, which would mean going to the upper cell, meaning going from grid at ij to grid at I minus 1j. Notice that there could be some signs on these cells of the grid that point outside the grid, meaning that point out of bounds. So we'll initially start at the upper left cell, which is coordinate 0, 0, and a valid path in the grid is a path that starts from the upper left cell, which is again the top left cell 0, 0, where we start from, and it ends at the bottom right cell, which would be m minus 1, and n minus 1, keep in mind m and n are the dimensions of the input grid, kind of like the number of rows and columns, right? And following the signs of the grid, and the valid path does not have to be the shortest. It just simply has to be the minimum cost, as we see here. So we can modify the sign on a cell with cost is equal to 1, and we can modify the sign on a cell exactly one time only. So we need to return the minimum cost to make the grid have at least one valid path, right? It has to have at least one valid path, and it also has to be a minimized cost solution. So in example 1, they also give us an image to better visualize this. As we see, we have a 4x4 input grid with different signs or arrows pointing to which cell to go to. At that specific cell, we see we'd have 4 1s, 4 2s, 4 1s, and 4 2s, in this case signifying the different arrows that we have. Now, in this case, our output is 3. Well, why is that? Let's go ahead and analyze how this matrix is actually going to work by modifying the specific values to minimize our cost to have that valid path from 0, 0 to m minus 1, n minus 1. Okay, so why is our output 3? Well, first of all, we'd start at the point 0, 0, the upper left cell, and the path to 3, 3, as we see at this last cell here, would be as follows. First of all, we'd go from 0, 0 to 0, 1, then we'd go from 0, 1 to 0, 2, then we'd go from 0, 2 to 0, 3, and change the arrow to down with a cost equaling to 1. So now it would be from 0, 3, 1, 3, and then we'd go from 1, 3 to 1, 2, from 1, 2 to 1, 1, from 1, 1 to 1, 0, and at that 1, 0, we'd then change the arrow to down, we change the arrow to down, right? Basically, we'd have a cost now to be another 1. Now we'd have, instead of 1, 0, we'd add a 1 there for the cost to go down, or rather for the direction to go down, and cost equals 1 to 2, 0. We'll go from 2, 0 to 2, 1, 2, 1 to 2, 2, 2, 2 to 2, 3, and from 2, 3, we'll change the arrow to down with another cost of 1 to be, instead of 2, 3, 3, 3, and we're there, right? From 0, 0, we went to 3, 3. Now this may have not been the shortest path, but we don't care about the number of nodes we visit. We only care about the cost that we actually maintain and try to minimize as we actually visit the nodes. And in this case, we can't have a total cost to be less than 3, since that is the minimal option to reach 0, 0 and go all the way till 3, 3, we'd have an output of 3. In example 2, we have an even smaller dimensioned matrix. We have a 3x3 input, with our grid to be 1, 1, 3, 3, 2, 2, and 1, 1, 4. And in this case, believe it or not, our output is actually 0. We literally can follow the path from 0, 0 to 2, 2 without having to actually have a cost of changing any cells. We don't have to change a cell. We can go from this guy to this guy. You go like this, right? Kind of following the arrow's direction, right? So we'd go from 0, 0 to him, to this cell, to that cell, and to the right one more time to get from 0, 0 to 2, 2. Okay? And finally, in example 3, we have our input grid to be 1, 2, and then 4, 3. And in this case, our output is actually going to be 1, right? We really only have to change a minimum of exactly one cell to be able to reach the top, or rather to be able to reach the bottom from the top cell. Okay? So for the constraints here, we see that M and N are going to be the grid length, basically the number of rows and columns, and we see that the dimensions of this grid, basically M and N, are not going to exceed 100, and of course be non-zero or non-negative, meaning at least 1, and we see that any value at grid index I index j is always actually going to be valid, meaning either 1, 2, 3, or 4, having an actual valid direction to go to, so we won't have to deal with any invalid inputs. So with the problem statement, constraints, and examples out of the way, I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution, and then I'll show you guys how I would optimally solve this problem in a few seconds. Okay, well, what is one very important observation that we can really make here to solve this problem pretty efficiently? Well, that observation really is that, of course, we need a way to minimize the cost while we actually explore all the different possible paths while also being efficient, right? And think of an algorithm that would really help us here. And in this case, we're going to use a modified version of the breadth first search algorithm, also known as BFS. Right? Basically, we're prioritizing paths with lower cost, right? So, on a high level, how is our solution structure really going to look like? Basically, again, the algorithm that we're going to be using is going to be inspired as such by BFS, but instead of just using a regular queue, we're actually going to be using a priority queue, or also known as a deque or double-ended queue, to actually implement a 0-1 BFS. And what that really means is that it's going to allow us to explore the cheapest paths first, actually further optimizing our process of the BFS algorithm. So what is the kind of solution structure as such for this code? Basically, first of all, like we just talked about, we're going to use a double-ended queue or a deque to store these cells that we actually visit iteratively along with their costs. Right? Then we're actually going to start at the top left corner with an initial cost of 0. Right? And then we're actually going to use a visited array to avoid revisiting any cells unnecessarily and having any redundant repeated computations. Then we're actually going to explore the 4 possible directions. Keep in mind that would be 1, 2, 3, or 4 in this problem, or generally just right, left, down, or up. And if moving in the same direction as the cell's value, if it costs nothing, we can just push it on to the front of the queue. However, if we actually change the direction, it would cost 1, and so we'd have to push it to the back of the queue. Right? So again, for the data structures as such, we're going to basically have a deque to store the pairs of coordinates and their corresponding costs in the input. And we're also going to have a visited matrix that makes sure that we don't revisit cells that we've already processed with a lower cost. Right? So now let's go ahead and dive straight into the code here. So like I talked about before, we actually do want to use that double-ended module, rather data structure, and this isn't really necessary in the Leetcode editors specifically, but I like to do this for best practice. I'm just going to import the deque data structure from my collections module. This is actually a very important module to be familiar with, apart from just Leetcode in general. It has a lot of very important data structures, also like the counter dictionary, right? Basically to store every single character with its corresponding frequency in a iterable, right? But again, to get back on track, basically from the collections module, we're importing the double-ended queue data structure, right? Again, this deque is very, very crucial for actually implementing our 0-1 BFS very efficiently. Why? Because it really allows us to add elements to both the front and also the back in constant time. Okay, so now that we've covered that portion, let's actually get into the main chunk of the code here. So what I usually like to do first in the beginning of my matrix problems is I just like to store the number of rows and columns, basically the M and N or dimensions of the input grid in rows and columns integer variables. So that's exactly what I'm going to be doing in this problem as well. I'm going to set rows and columns to be the length of the grid and the length of the grid at index 0 correspondingly. That's a pretty neat, efficient way to get the number of columns in an input grid, right? It's basically going to help us iterate over the grid later on in the next couple of passes. Okay, so now let's actually initialize our directions array, right? You may be thinking, okay, what does this directions array really signify? Well, let's actually think about it. We're given that we have 4 different directions to go to, either left, right, up, or down, right? The 1, 2, 3, and 4 integers at every single cell as a possibility, right? So basically, we're going to actually define here the 4 possible directions that we can actually move in the grid, right? That would be, again, right, left, down, and up. In this case, they're going to be stored as coordinate offsets, not coordinates themselves, but rather coordinate offsets to move in those corresponding directions in the form of length of 2 tuples. So in this case, we have 0, 1 as the first coordinate offset. We also have 0, negative 1. We also have the possibility of going 1, 0 for the corresponding xy cell, or we could go negative 1, 0 for the final direction of the xy cell. Right, again, the 4 possible directions that we can move to as a coordinate offset from the current cell index or cell value. Okay, now let's actually initialize our double-ended queue. I'm going to call it deque, and it's going to be initialized to a double-ended queue. And for the initial parameters as such, what we're going to be passing in is 3 zeros, right? And what these 3 zeros really signify, again, before we actually get into that, we're initializing this double-ended queue. I'm just going to call it deque, and it's going to have initialized a tuple of length 3. Very important. Now, let's get back to the main topic here, the main question. What do these 3 zeros really signify? Well, first of all, these first 2 elements, or these first 2 zeros, would represent the starting cell and the ending cell, and the third element, or this final 0, would represent the initial cost. Right? That's the initial cost, and that cost for that specific cell, of course, for the 0, 0, that would literally just be a cost of 0, right? We don't need to do anything to get to that cell because we literally start at that cell. Okay, now let's actually initialize our visited array here. It's going to be equal to false initially, right, times the number of columns we have in the range, I don't need the parentheses there, in the range of the number of rows we have. Okay, again, kind of initializing this visited 2D table here. It's going to be a 2D array that's having all the elements initialized to false with dimensions of rows and columns, and basically it's going to track whether we've actually already visited a cell in the input or we haven't. Okay, so let's actually begin our actual BFS here, our BFS loop. Standard while the double-ended queue is non-null, right? Basically, we actually continue on as long as there are actually cells in the double-ended queue, meaning it's non-null and it does actually have nodes to check. We still have to process and parse the data structure. So while deque is non-null, we're going to do something called unpacking in Python. We're going to get the cost and the x and y coordinate to be the deque.popleft method here, right? Basically, sorry, I forgot my deque. Sorry about that. But basically what we're really doing here, again, this is really unpacking in Python. We're dequeuing an element from the front of the queue, right? That's going to give us the current cost and the row x and the column y for the current coordinate for processing. And we're going to store those values in the corresponding variables cost, x, and y as we actually pop those 3 values, or basically tuple of length 3, and store or unpack those specific values in these corresponding variables cost, x, and y. Now, the first thing we have to check once we actually pop off this element here, or cell I should say, if visited at this cell as such, x, y, if it's already true, and in this case I could just say equal to true, meaning we've already visited it, or I could just do this. In Python, doesn't really matter. If that's the case, if it's not actually false, we immediately want to continue, right? That means the current cell, x, y, has already been visited, and we have to skip it to avoid any redundant computations, any repeated work. Okay, well, now in this case, if we haven't already continued, if we haven't actually already checked that, we've already made sure that it isn't actually been visited, now that means we're going to use it in this iteration, we're going to visit it in this iteration, and so we might as well set it in the visited array at this coordinate to now be equal to true, because we literally are going to now mark the current cell as visited and actually process it in the current iteration. Now, the next conditional that we're going to have here is basically if x is actually equal to rows minus 1 and y is actually equal to columns minus 1, great, we want to return cost. Why might we want to return cost? Well, let's go back to the example here. We want to go, or rather end, at the bottom right cell after we minimize the cost for the current valid path. What is that bottom right cell? Well, that cell is going to be m-1, n-1, right? It's going to be the literal most bottom right cell in the input grid. In this case, that's exactly what we're checking here. If x is equal to rows minus 1 and y is equal to columns minus 1, that means our current coordinate x, y is the bottom right cell. That means we've actually reached the bottom right corner of the grid, and so we can return the current cost, whatever it is, because at this iteration, it would be the minimum cost to get there. Okay, great. But what if we haven't already explored or hit the very last cell? What if we haven't already returned cost and we haven't actually already visited this current coordinate or cell xy? Well, in that case, now we actually have to calculate the new coordinates in the 4 different possible directions that we have. And the neat way to do this in Python is basically using a for loop here, of course, for every single I and dx and dy in the enumerate. I'll explain exactly what the enumerate does in a few seconds of the directions. And for our second parameter, we're going to go for 1. Basically, it's not very standard here to use this syntax in Python, I am aware. To really explain what this does, first of all, what does enumerate do? Basically, it's a standard for loop syntax. However, it actually keeps track of the current index along with the current character's value. Basically, again, we're looping through all the 4 possible directions, which would be right, left, up, and down, in this visited coordinate offset array, or rather, sorry, in this directions coordinate offset array, right, in this for loop here, right, where each direction actually has an index I corresponding for its value, or corresponding to its value. That's what the enumerating part does, right? Basically, it would be 1 for right, 2 for left, and so on and so forth for up and down as well, okay? So basically for every single iteration in these 4 possible directions, or for every single possible unique direction, we'll get the new x value and the new y value. For shortening of the variables, I'll just call them an x and an y. They're going to be x plus the current coordinate offset dx, and y plus the current coordinate offset dy, basically going in that specific direction. We're calculating the new coordinates, nx and y, by actually applying those directions offsets in every single iteration of this 4-directional loop. Okay, great. Now that we've actually initialized and got our new coordinates, now we actually have to check if we've visited them or not, and if they are actually in bounds. So way we can do that is a little bit lengthy, but first of all, we have to actually make sure that these variables or cell values are actually in bounds of our input grid, and we haven't actually visited them just yet. So if the current basically row value or row coordinate index, if it's actually at least 0 and less than rows, meaning it's in bounds for that specific row, and very similar logic for the y value, basically the column cell value. So if that's at least 0 and less than the number of columns, meaning it's in bounds for both the rows and columns in the entire input grid, and we haven't actually visited the current cells, we can check that by simply saying and not visited nx and y. Keep in mind those are our new coordinates. Sorry, there should be an ny there. In that case, if that's the case, what are we really checking here? Well, again, to reiterate, before actually processing this new cell at x and y, we have to first make sure it's within the grid's boundaries. So it's nx is actually within the number of rows and 0, and ny is equal actually within 0 and the number of columns we have, and we haven't actually visited just yet. And the simple way to check that is and not visited nx and y, basically checking if visited at this cell is false or not. Right? So if this is not the case, or rather if this is the case, that means it passes all of these 3 criteria, and so we can actually calculate the cost to move on to the new cell from this current cell, right? So we'll get the new cost, initializing it down here on line 19. It's basically going to be the current cost if grid at xy, right? If grid at xy, if that's actually equal to the current index I, else it's simply going to be cost plus 1, right? This is kind of the changing direction part if required. Basically, again, to reiterate, we're simply calculating the cost to move on to the next cell from this current cell xy. And now, first of all, what we're really checking here is kind of a ternary operator, I believe is what it's called. Basically, we're going to have a conditional on one line. Effectively, what we're doing here is we'll set the new cost to be the current cost if the grid at index x, y is equal to I, meaning if the current cell's direction actually matches I, well then of course that's great, the cost would simply remain the same. However, if it's not actually matching directions, we would actually have to change its direction to help us move to the current path, the valid path, and go to the last cell, and so we'd actually have to add 1 to the cost, kind of simulating that operation where we do have to actually change the direction. Okay? Now, once we've actually got the corresponding new cost, if the current grid at xy if it's actually equal to y, well, then in that case, we want to append to our q. So deque dot append. In this case, it's not just dot append because this is a double-ended queue. So we do have, in fact, let me actually explain that before we move on. What a double-ended queue really does is it allows us to either append from the left side or the right side, both in constant time. And we can also pop not just append from both the left and right sides in constant time. And that's what really makes it very helpful for such graph problems like this. But effectively, going back to our solution here, we're going to set deque q dot append, in this case appending to the left of the data structure, a tuple of length 2, or rather of length 3, the new cost, the nx new x variable or x coordinate, and the new y variable or y column cell value. Okay, now if that isn't the case, meaning if the current direction doesn't actually match, if it's not actually equal to I, so in the else conditional here, we simply have deque and append it regularly, so basically to the right, the same thing, the new cost for this corresponding cell here, up until this current cell to move to that direction, nx, and then y, the new xy coordinates of the current cell. Right? So very similar structure here as what we just discussed. Effectively, we're using that 0, 1 BFS logic. If the direction actually matches, or if grid index xy, if it's actually equal to I, the current direction matches, we can add the cell, or rather we can add the new cell nxny to the front of the deque to actually prioritize that cell, minimizing the cost. Otherwise, if that's not the case, we simply add it to the back, meaning we have actually changed the direction. If it's not equal to I, we have actually changed the direction. We did actually increment the cost by 1. Okay? And effectively, that is the entire code here. If I were to submit this, unless I made any syntax errors here, this should be accepted and this should be a valid solution. Okay. Probably made a very silly mistake here. Let me just make sure I didn't do anything. Okay. Yeah. So this should be directions, not direction, because I initialized that array to be directions instead of just direction. Sorry about that. Now this should be a valid solution. This shouldn't be accepted. Okay. Let's see what happened here. deque.append. Let's exactly see what the error here as such is. Sorry, this should be q. Yeah, so just classic me for forgetting to remember that our deque was actually initialized to be deqq and not just deque. Sorry about that, guys. A couple silly mistakes like I talked about before. Now this should be a valid solution. Now this should be accepted. And as you can see, this really is literally just about as efficient as you can get, beating nearly 100% of users, both runtime and memory or space complexity-wise. So, to kind of reiterate what we're actually doing here, effectively overall, we're actually using the 0, 1 BFS logic to actually explore all the different possible paths in the grid, while also simultaneously minimizing the cost as well. And effectively, by prioritizing the moves with no additional cost in our queue, our double-ended queue is going to make sure that we always find the shortest path efficiently and append nodes with that corresponding changing directions accordingly. So for the time complexity here, this is actually going to be a big O of n times m solution, nm if you will. N is going to be the number of rows, and m is going to be the number of columns. Very simple reason why. This really is just a one-pass solution here. We're going to iterate over or process every single cell at most once in the input. And the memory or space complexity is going to be big O of n times m as well, because we are actually using auxiliary memory and extra data structures for this visited array, 2D array, which is our bottleneck, and also this double-ended queue, which does also take up extra space as well, which do actually grow directionally proportionally to our input size, right? So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.